Hi, everybody. I hope you had a great night. Today's video very short. We're just wrapping up the chapter. I know we're actually ahead of the notes, but that's fine. I'll give you a little bit of rest time. We're just wrapping up the chapter with a couple of example problems on equilibrium and a couple of sample AP problems, just so you can sort of see, all right, what kind of things could they ask us about equilibrium and conservation of angular momentum? So take a look at this situation. A cable is attached to the midpoint of a horizontal beam of length L. What's the tension in the cable and the force at the hinge where the blue dot is? Well, first of all, first thing you do is always draw your force diagram. Center of mass should be right at the middle of this, and the force of gravity, let's go with 9.8 meters per second squared for gravity, would be 98 newtons. And now to solve it, remember my trick I sort of showed you earlier? Yes, I realize that counterclockwise torques are positive, clockwise torques are negative. But if we just look at their magnitudes, if this thing's in equilibrium, the magnitude of the counterclockwise torques must equal the magnitude of the clockwise torques. Plugging in our numbers, this tension right here would tend to rotate this thing counterclockwise relative to this pivot point. So the torque produced by this is the force times the distance half the length times the sine of the angle between it, which is this 45 degrees. And the force of gravity here would be trying to rotate this whole beam clockwise, so the torque due to it would be 98 times, again, half the length. Solving that real quick, you'll discover very quickly that the tension's about 139 newtons. Putting that in there, we can then break the tension into its vertical and horizontal components, in this case, both 98 newtons. And so now we can ask our question, all right, what's the force acting on the hinge? Well, if you look at this very quickly, you'll notice, hey, wait a second. The sum of the vertical pieces here are already zero. See, the only thing we need to worry about is this horizontal component of the tension that's trying to push the rod into the wall. So what must be the other force acting here? We must have 98 newtons pushing outward from the wall. And that's all of our forces. So we've got 139 newtons of tension, we've got the force of gravity, and we have this outward force on the hinge. And together, not only does that produce a net torque of zero, but it also produces a net force of zero, which, remember, those are the two requirements for equilibrium. All right, what about a little bit more complex problem? In this case, we've got a large mass sitting over here, and we still have a 10 kilogram beam, we still have the wire here, and the question is, what's the tensions acting over here? And again, drawing our forces, this time we've got the tension, 98 newtons acting at the center of mass, 196 newtons acting on that mass over there. Doing our torques, again, first of all, treating this blue dot as our pivot point, we have just one counterclockwise torque, this tension that's trying to rotate this thing counterclockwise, and we have two clockwise torques. This force and this force are both trying to rotate it clockwise. Now, officially, I realize the tension here, if this is stationary, has to be 196 newtons, which means the tension over here has to be 196. But I just simplified it and just said I just used this 196 down here at a length L from the pivot point. Solving this, you'll get a tension of 693 newtons in this case. If we break that into its vertical and horizontal components, you'll discover in this case that they're each 490 newtons. Now, you're like, okay, this is really simple. But we've got an interesting problem here. Yes, the horizontal here is going to be exactly equal to the horizontal here. That balances all the horizontal forces so that they balance out to zero. But here's the issue. The upward component here is 490, but yet the sum of these two is only 294 newtons acting downward. We've got a greater upward force than the sum of the two weights. What does that mean? That means at this blue pivot point over here, we have to have a downward force of 196 newtons. Why? This 196 plus this 98 plus this 196 adds up to 490 to exactly balance that. So what's the force here? Well, if you do a quick little Pythagorean theorem, this is a right triangle, you'll find the hypotenuse here must be 528 newtons acting downward like this. And yes, I realize you could solve for theta here, doing a little bit of trig, but in this case, I'm just interested in the magnitudes. So this force, along with these two weights, along with the tension, produces equilibrium, where the net torque is zero and the net force is zero. All right, change of pace. In this case, a clay ball, this is that blue ball right here, is moving at 10 meters per second, and it's moving towards a 1 meter long rod that has a mass of 1 kilogram that's suspended from its top. If the clay ball sticks to the rod, what will be its initial omega after this thing sticks? In other words, what is going to be omega as this thing starts rotating around this point? And then finally, to what height will this rise afterwards? Oops, sorry, there's the bell. Ignore that for a moment. This should remind you sort of the ballistic pendulum from the momentum conservation chapter. And yes, it turns out you can use angular momentum for the first part of this, because yes, we can't just use energy conservation all the way through. Why? Because when this hits, it's going to generate some heat, E-dis, but we don't know how much. So we can, but angular momentum has to be conserved, just like regular momentum has to be conserved. And then after we figure out omega, we can use the conservation of energy to go from this step over to this step. All right, solving this. Angular momentum initial has to equal angular momentum final. And in this case, this is a point mass that's moving with some velocity. So I'm going to use the other form of angular momentum, which is mv/r perpendicular. And over on this side, because it's just an object rotating, I'm going to use I omega, the standard form of angular momentum. But we've got one interesting problem. What's the rotational inertia of this rod? And you might say, oh, it's in the table. Rod pivot at one end is 1/3 ml squared. But we also have this mass, this clay that's stuck down here at the bottom. So to solve this one, the total rotational inertia of this thing is going to be the rotational inertia of the rod plus that of the clay. The rod, of course, 1/2 ml squared plus, for the clay, I'm just using mr squared, the basic definition. I'm treating it as a point mass. So its mass is 1, and it's 1 meter away from the pivot point. So the rotational inertia in this case is 4/3, and I left off the units here just because I ran out of space. I guess they're kilogram meter squared. And now I can solve this part down here. So mass, velocity, radius for the clay blob equals the rotational inertia of this system, which is 4/3, times omega final. And if you solve that, you'll discover that this thing is moving with an omega of 7.5 radians per second after the clay blob hits and sticks to it. If you check the energy, the kinetic energy here compared to the RKE here, you'll discover that we've actually lost some energy. Where to go? Into E-dis. All right, now the second part. Conservation of energy, going from here to here, what kind of energy do we start out with here? Well, we've got an omega. So most of you probably go, oh yeah, it's RKE, rotational kinetic energy, being converted into GPE. Plugging in our formulas, remember rotational kinetic energy is 1/2 I omega squared equals GP, in this case, the mass of the rod is now 2 kilograms. The sting, or the rod plus the clay, times 9.8 mg times the change in height. And if you solve this one, you'll discover that the center of mass of this system is going to go up 1.91 meters. That's actually quite a ways. I drew it, didn't even draw it here all the way. If the center of mass of the system, just to talk about it real quick, the center of mass of the rod was here, the 1 kilo, and that's 1 kilogram. This is 1 kilogram. The center of mass is actually right about here, 3/4 of the way down, a little bit over. That's actually going to go up 1.9 meters. It's actually going to swing all the way around. Oh my goodness, quite a ways around. A brain break? I'll give you 5 seconds to pause the video. Give it a quick try if you need a little brain break. See if you can get any of these. And I'm going to count down to 5, and then I'll show the answers. You can restart it after you give it a quick shot. Let me read this. Each answer is a 7-letter word or name that ends in the letter O. Each letter starts with a different letter of the alphabet. Canadian province. Ontario probably would work. Let me double check that one real quick. Yes. Okay. And then, Hitchcock film. Psycho doesn't work. I know. Okay. Give this, see how many you can solve. Again, remember, this is a Mensa quiz. 5. There's the bell. 5, 4, 3, 2, 1. Tabasco. Keepsake is a memento. Hitchcock film is Vertigo. I figured that out just beforehand. Inert medication is a placebo. Below freezing, Sub-Zero. Hellfire, Dante's book. Dante refers to the Inferno. Big talk, fake courage is bravado. Spicy sausage, chorizo. I didn't know the last one at all. All right. Here are some actual AP problems. And I'm not going to talk it through too much. I'm just going to do a countdown before I show the answer so you can pause and give it a chance, or give yourself a chance to think about it. 5, 4, 3, 2, 1, 0. And what's happening here? In this case, as Mars is moving around from its sun, gravitational potential energy is increasing, but the angular momentum, which is MVR, must be conserved. So the correct answer is B. Oops, I pressed the wrong button. Take a look at this one. And this is related to one of the problems we did already in this one. I'll let you read it, and then I'll show the answer in 5, 4, 3, 2, 1. Which one would make the force on the wall as small as possible? Moving the support cable to the center so it's holding up both the weight of the beam and the weight of the mass will actually make the force at the pivot point smallest. It's sort of like what we had when we earlier on. If you remember, there was no vertical forces when we had that. This one has 2 solutions, and I'll show you the answers in 5, 4, 3, 2, 1. Yes, of course, doing it this way. I should first of all explain what's happening here. They're trying to figure out the torque. How can you figure out the torque? Well, remember, torque is equal to I times alpha, the angular acceleration, where these two are in the same direction. In this case, they're trying to solve for the torque, and they know the rotational inertia. So what they need to find then to solve this is angular acceleration. And they're spinning it up to a known initial angular speed. So if they knew how much time, they could very quickly figure it out because it's the change in omega over the change in time. The second answer is B. Why? Because they could use the equivalent of this. V final squared equals V initial squared plus 2A delta x. Or in this case, omega final squared equals omega initial squared plus 2 alpha d theta. In this case, they know the initial. The final is 0. It comes to rest. If they knew this, they could calculate alpha as well that way. AP will have 5 questions in the multiple choice section, and they'll identify them, which will have more than one answer on them. This last one is more of a short answer problem. In this case, there's a ladybug that's initially on the edge, and this thing's spinning once every 2.5 seconds. Later, the ladybug walks closer to the center, and then it spins once every 2 seconds. Part 1, derive an equation for I2 in terms of I1. Again, pause the video, let you think about it for a little bit, and I'll show you the answer in 5, 4, 3, 2, 1. You could try doing it mathematically, but we don't know the mass of the disk, which makes it a little bit painful. But what we do know is we can calculate the angular velocity before and afterwards, and if we know that angular momentum is conserved, we can use this idea. So I1 times omega 1 has to equal I2 times omega 2. Now you might say, whoa, wait a second, we don't know omega. Well, remember omega can be written as 2 pi over the period. We did this before in this chapter, or you can write it as 2 pi times the frequency. That's an F, believe it or not. And so if we do that, we can simply write omega 1 is 2 pi over 2.5 seconds, because that's how long it took initially to go around. And then omega 2 is 2 pi over 2 seconds, because that's how long it took to go around later. Solving that, you can rearrange it a little bit. I'm multiplying both sides by 2, dividing both sides by 2 pi, gives us that. Or our answer in this case simply is this. So what's an equation for I2 in terms of I1? I2 is just equal to 4/5 of I1. Then finally, while the ladybug is walking towards the center of disk, does it exert a torque on the disk? And the answer is no. You can think about this in a bunch of different ways. The ladybug actually is exerting and has to pull itself inward as it walks. What equal and opposite forces that apply to the disk, it applies it that way. So you could simply state that the force applied by the ladybug should be along this radius vector. The torque, which is force times r times the sine of theta, in this case, theta is 0 degrees, and so there's no torque. The other way I just could explain as well is that there's no external forces on the system that could create a torque on the disk. The only force there is the ladybug, and it doesn't generate any torque at all. With that, I'm done. You've got a couple more homework problems tonight and some worksheets to work on. The video, again, very, very short. There's office hours coming up. Please just drop in if you have any questions or you want me to show things, or just hop on the WeChat group and say, hey, Mr. Clymer, how do I do this question on such and such worksheet or on this page? Have a good night, and we'll talk to you soon. Bye.